Okay, so let's start. Welcome everyone. Today our speaker is Yu Cheng. Yu Cheng did his PhD from University of Southern California, advised by Shanghua Tang. Now he's a postdoc at Duke University. Yu Cheng's research interest is in intersection of game theory and machine learning, and today he's going to tell us about non-convex matrix completion. Yu Cheng.
Thanks for the introduction, and thanks for having me here. I really appreciate you guys showing up here rather than attending the the retirement talk next door. And I'm going to try to wrap up this as quickly as I can so we don't miss the party or something. So good. This is a small audience, so feel free to interrupt and ask questions. So it's more. I'm treating this more as a seminar thing, even though the talk is recorded. Good. So today I'm going to tell you about non-convex matrix completion. This is a joint work with Rong from Duke University. So in recent years, non-convex optimization has become quite successful in practice. Like multi-layer neural networks becomes the dominating approach to many problems in computer vision and speech recognition and many other things. However, the theoretical analysis of non-convex optimization still lags behind. Recently, there has been a lot of attention to try to improve our understanding to non-convex approaches, governed by this question, basically, can we explain why they work very well in practice? And some of the questions you can ask in this regime, for example, you could ask, are all the local optima approximately global optimal for some given objective function? And can you understand the structure, geometry of the objective function? Can you use that to design faster algorithms? So this talk, half of this talk belongs to non-convex optimization. The other half belongs to spectral graph theory, for lack of a better name. So this is a field that bridge together discrete and continuous optimizations. So if you look at two separate fields, one is like graph theory, which studies discrete objects, which has combinatorial algorithms. They studies graph trees, paths, flows. And the other, you have like numerical analysis tools where people do iterative algorithms, look at matrices and eigenvectors. And together, recently there has been quite a lot of success in combining these two fields to produce faster algorithms for electric flow, say solving SDD linear systems, max flow, better solver for linear programming, and many, many other problems. So the other half of this talk would belong to spectral graph theory. So this is roughly where this work comes in. This is a high-level big picture. So now I'm going to dive into the problem definition and what I actually want to do about matrix completion. Good. So in the matrix completion problem, you have an unknown m by m matrix of rank R. And the input to the problem is a subset of entries revealed to you. Sometimes people assume it's uniformly at random, independently, with some probability. And your goal is look at those entries and try to recover this low rank matrix. Okay. This is a basic machine learning problem that has applications to recommendation systems and collaborative filtering. For example, you could think of the rows of the matrix as users and columns as movies. And if you observe an entry, it means in your system, a user rated a movie, gave some score to that movie. And the underlying low rank factorization just means every movie has some features and every user has their preferences. Okay. Good. So throughout this talk, we're going to assume the underlying matrix is incoherent. That is basically to avoid this degenerate case where there's only, it's a very sparse matrix, somewhere is 1. So the assumption just says all the singular values should have similar norms. And we're going to assume all the observations are noiseless. So no noise added, just try to recover this matrix. Good. So traditionally, like the most classic approach to this problem, at least with theoretical understanding, is convex relaxation. So you can formulate this as minimizing the nuclear norm of the matrix, subject to that matrix agree with all the observation you have. Okay, so nuclear norm is just the sum of the singular values of M. So what you actually wanted to do is to minimize the rank of the matrix, subject to this constraint, but this is NP hard. So instead of minimizing like the L0 norm of your singular values, you just do L1 norm instead. Okay? And you can show that if all the entries are observed uniformly at random and with sufficient probability, then this convex program will give you the exact solution. Okay? Will recover M, and it can be solved. It can be basically rewritten as a SDP and solved in time n to the 4. Okay, not fast enough in practice, so we're not happy with that, and that's why in practice mostly people use non-convex heuristics. And the most intuitive non-convex objective function is just to solve for a variable x that has the same underlying dimension than the low rank factor, and you just want to minimize like the least squared error with the observations. Okay. So there has been a lot of work on trying to understand why a non-convex approaches works very well for matrix completion in practice. So in the beginning, the earlier works focus on what happens if I can have a careful initialization, mostly from SVD. So basically, there are a lot of work showed that if you start at the right place, then run gradient descent, you're going to end up at the ground truth. And then later, there are more work giving like a framework-based approach for this problem that showed like strong convexity near the global optimum, so that a lot of the algorithm would actually work. And more recently, people have been looking at doing just gradient descent without some special initialization, basically start anywhere, and to show that this function has no bad local optima. I think Teng Yuma was here presenting some of the work about 2 years ago, a year and a half ago. Good. Right, so basically these are some of the previous work on convex and non-convex matrix completion. But the crucial thing which motivated our work is that all of these papers on this slide needs to assume that all the samples are revealed, all the entries are revealed to you with the same probability p. Okay. And in this talk, we just want to ask the following very simple question. That is, what if they are not observed with exactly the same probability? They're just observed with at least probability p. This is a more realistic assumption in practice, because let's say a certain group of your users might want to reveal a certain subset of items more often than the other people, right? For example, maybe man likes to reveal I don't know. Something, but and a woman likes to review shoes or something. But so it's very surprising to me, at least, why people haven't been asking question this old assumption that the probability are exactly the same. And on the other hand, this is actually very related to another model where a semi-random adversary can look at which samples are revealed to you and then reveal additional entry to you to try to introduce a bad local optima in your objective function. Okay, good. So the question we want to answer here is, are the previous non-convex approaches robust in this semi-random model? And if not, is there a way that you can fix them, but also still make them faster than the convex approaches? Good. So this talk, from now on, this talk will be these 3 parts. So the first, we're going to show that 2 counterexamples to the previous non-convex approaches basically tell you that it's possible that they can get stuck in a bad local optima. And even if you want to do careful initialization with SVD, it might give you a totally wrong subspace. And then we're going to introduce a pre-processing step that tries to reweight the entries so that the input becomes random. Basically try to undo what the adversary did to the input. And then eventually I'm going to prove to you that after this pre-processing step, that the non-convex objective function has no bad local optima. Okay, good. So now let me first do the counterexamples. Okay, good. So this is the recall the non-convex objective function. So the counterexample just works like this. I'm writing them as 2x2 matrices, but they're actually block matrices. So each one should be multiplied by all ones matrix of size n over 2 by n over 2. And P is the probability that you observe this entry. Okay? Basically, you're much more likely to observe entries from these diagonal blocks than the off-diagonal blocks. Okay? And X is the bad local optima that I'm going to get stuck at, which is roughly equal to this number. Okay. So the way we can verify that there is a bad local optima near X is to basically say what's the expectation of M star conditioned on the revealed entries. Okay, because these entries are revealed with much higher probability. This is what you essentially get if you take the expectation. When all the entries are observed with the same probability, this expectation is exactly equal to M star. But now it's different. And that's essentially the reason why you can take this matrix and plug in that the expectation of first order derivative of fx is 0, and the Hessian is PSD. That means if P is high enough, then there will be a bad local optima near X. Okay? And roughly speaking, the reason why this is happening is because the sampling is biased, so that the actual thing that you observed is biased because of P. And U becomes a local, sorry, it should be X. So X becomes a bad local optima because it's an eigenvector of this matrix. Okay? It's not rigorously true, but that's roughly what's going on here. Okay?
Sorry,
yes?
I did not understand at all. Why do we care about the expectation of M star?
Because this is the objective function that you're using.
Yes.
And right, basically you can take the expectation of fx, and the probability of ij in that's observed is given by the big P matrix.
Yes.
And that's why.
But I guess the thing I don't understand is the fact that these do not have bad local optima. It's a high probability statement.
Yes, when P is high enough, then first of all, if all the samples are given uniformly at random, when P is high enough, then no, you don't have bad local optima.
Yeah. So I just don't get how on a 2x2 example.
Oh, it's not 2x2. They are 2n/2, and I'm just writing out.
I didn't understand. So can you explain again? Just
right. So basically, all of these matrices are n by n. But I'm partitioning them into equal size blocks, and I'm writing out the number for that block.
Okay, cool.
You should take that number and multiply the all ones matrix and fill it in there.
Okay. I see.
Right. Okay.
Yeah. I
Okay, good. So right, that's roughly what's going on. So this is the first counterexample that shows when ij is not sampled uniformly at random, then this function could potentially have a bad local optimum even when P is very large. And another example we have in the paper that I'm going to omit here is we have a 4x4 block matrix that shows you if you do SVD on the observed entries, then that's not going to give you the right subspace. And what I mean by that is the angle between the subspace that you get from m dot p. Again, this is like the expectation that you observe. And the true subspace, the angle between these subspaces is 90 degrees. So they're actually orthogonal to each other. So these together are bad news. It essentially says you have no hope of doing some careful initialization because you're going to get totally wrong subspace. And if you start from a random point, then you may end up in one of these bad local optima. That's essentially induced by the sampling probability matrix rather than the ground truth. Okay. Right. Questions? Yes. Okay, good. So good question. So the question is, what about other approaches? If I don't want to do, like gradient descent on this function. So for example, the first thing I should say is convex approaches still work. The previous nuclear norm minimization program, that still works. Because given additional entry would not change the optimum of that function. So that will still give you the m star back. Like Jonathan was asking about SVD. It depends. There are some previous work on deterministic conditions, like do matrix completion on deterministic conditions. But they use convex approaches as well. But they didn't solve the entire thing. They used some other. But it's in the paper. Good. But yeah, for this talk, we're going to specifically focus on just do gradient descent on this function and ask, can you do something to the input so that you can avoid the bad local optima? Okay, good. So now let me tell you about our preprocessing step. So good. So basically, we'll look at the first counterexample and ask ourselves what went wrong. Okay? So what happens is if all the entries are revealed with the same probability, this is roughly what you expect to see from a matrix. But in that counterexample, the diagonal blocks are much more likely to be observed than the off-diagonal block. So you see something like this. Okay? And let's say if the adversary tells you that he's changing the probability like this, then what can you do? Can you do something to recover m star exactly? So one thing you can do is you can pretty much just resample this diagonal block. Okay, so for example, you just keep roughly 10% of the elements here, right? Then what you get is essentially like a uniform sample. Okay, or more generally, you can try to put different weights on the samples that you observe, so that the weight that you get from the diagonal and off-diagonal blocks are roughly the same. Okay? If you do this, then it's like your samples are coming from a uniform random distribution, and then you'll be fine. Okay? So the key idea of our preprocessing algorithm is basically to reweight the sample so it looks like a random input. And what do I mean by that is, first of all, this is a weighted non-convex objective function. So if you look at, if you take the graph view of this matrix, as in if I put an edge between node I and node j, if that entry is observed, this matrix basically corresponds like this graph. Okay, so it's a Erdős-Cheney graph with probability p, but then adversary added some additional edge to form these two very dense subgraphs. Okay, and our algorithmic task here is just to recover a Erdős-Cheney random graph. Basically, this is a graph that's like expander plus 2 cliques, and we just want to find some expander from that graph. Okay? And that's exactly the problem we solve in the preprocessing step. Okay? Questions? Okay. All right, so the graph formulation is the following. That you're given a graph G that you know contains a subgraph that's similar to some other graph H. And you want to reweight G so that the weighted version is spectrally similar to H. For matrix completion, H is just the complete graph or expander. This problem is, if you stare at it, it's very similar to a well-established problem in spectral graph theory. That is graph sparsification. So graph sparsification is a problem that gives you a dense graph that you want to produce a weighted sparse graph that has some good properties, has the same property, say commute time and a lot of other things with the original graph. Okay? And it's been first proposed by Spoon and Ten, where they showed that if you want two graphs to be epsilon close, then you need to take n over epsilon square edges. This tilde hides polylog factors, and m is the number of edges, n is the number of nodes. Then in a beautiful work of Batson, Spielman, Srivastava, they showed that you can actually get away with n over epsilon square edges this tight. And the running time has then been improved to nearly linear time. So the algorithm we use in this paper for the preprocessing is directly inspired by the recent advancement on this problem. Okay? And now I'm going to show you the formal formulation for these two problems, and hopefully you should be convinced that they are at their core they are essentially the same. Okay? So this is the spectral specification problem. I'm basically taking the vectors and multiplying each of them by L inverse half. That's the Laplacian inverse half power of the Laplacian, so that the sum becomes identity. So the spectral specification problem is I give you a bunch of rank 1 matrices whose sum is identity, and I want you to find a set of sparse coefficients so that their sum is approximately identity. Okay? It's the problem they solve. The problem what we want to solve in this paper is to say that I give you a set of vector, and I promise you there exists a subset of vectors that they sum up to approximate to I. And now I ask you to find a set of weights so that I don't have the sparsity constraint, but I don't know this hidden subset as well. Okay? So you can see that there are some differences between these two problems, but I'm going to explain to you why some of the solution for the first problem can be applied to our problem and some cannot. And hopefully that will be useful for you guys. Good question on these two formulations.
But this is the main step for your entire algorithm.
Right, yes.
Because after that you will just use the previous one. The third
Good. The pre-processing part is the main contribution of this paper. I think that's fair. Main technical contribution of this paper.
And you will also
yeah. No, I will say something at the end. But this is like before I work on this, this is the part that I couldn't see the most, and the rest are relatively easier, I'd say. Good.
So did you just say that problem 2 is not a simple corollary of problem 1?
No.
You can't, because you cannot do rescaling?
Right. For example, for this problem, the very first approaches are sampling by effective resistance, let's say.
Okay. You mean the second problem then?
The first problem.
Okay.
Sparsification.
Yeah.
That is basically if the graph is, let's say the graph is nice enough, it's a complete graph, then uniform sampling would work, right? But in our problem, there's an intuitive argument why any sampling algorithm basically shouldn't work, is because you can check this promise, right, in some sense. Well, I mean, you can check by running this. But when you're running, let's say you want to do, if you want to do sampling by effective resistance, it doesn't make sense on the second problem, right? You can probably. Right. Basically what happens in the second problem is you have an underlying graph, say an expander, and then I added some other extra edges into this graph, right? Which causes spectrum to change. For example, this graph is not an expander anymore. It contains an expander, but its mixing time in these two cliques are much faster than across the cliques. And in general, the underlying graph I'm trying to recover may not be expander. So.
Okay.
But you know, like.
So you can still do something.
Okay. We can take this offline. But I hope I can convince you at least offline that problem 2 is not a simple corollary of problem 1. Okay. Good. All right. So now let me take a slight detour to tell you about how people handle graph sparsification problem and why that routine is useful for us. Okay. Yes.
So your running time will be like n squared.
Why? The running time, I'll give you a nearly linear time algorithm for problem 2. Well, okay, good. For matrix completion problem, M doesn't have to be n square. You only need to observe roughly n log n entries. Yeah. But the adversary could add a lot of entries to your input, then M would be n square maybe. Or if the probability is higher than M is n square, then I can't do anything. Maybe I can do anything, but in this paper we don't study that. We just said that if you give me everything, I'm going to read it in first. You can run specification first, so you can always assume M is roughly like n log n over epsilon square. So, good. All right. So basically, the approach in Batson, Spillman, and Srivastava is they're going to maintain the current sum of these rank 1 matrices, and they're going to start with a equal to 0, and 2 barrier values that basically sandwich this PSD matrix A. So initially, L would be minus something, like minus a quarter or something, and U would be a quarter. So basically, right. So basically, in the very beginning, it's a 0 matrix sandwiched by minus I and I, and the algorithm will try to add edge iteratively and deterministically every time to grow this ellipsoid while keeping it away from the lower and upper barrier. Okay. The important thing for us here is the only thing you need to know about this algorithm is they actually add edge deterministically in each iteration. And why they're able to show that it works is they can say that a good edge always exists because you can take an average edge. Okay. So remember, in their problem, all the vectors sum up to I, which means if you take a tiny fraction of an average edge, so basically you take a tiny fraction of every edge, then your ellipsoid would just grow by identity. Okay, so you know that one vector is going to help you in the right potential function that you define. Okay, so basically you're going to start with basically the hope is the difference between the two variables are going to stay the same, but the barriers would advance at roughly the same rate and grow larger and larger, and this ellipsoid will become more and more like a sphere. Okay. That's the idea behind BSS. Okay. Okay, good. And I want to talk about this deterministically part. So basically, the algorithm can directly be generalized to handle our problem, because the argument that good edge exists holds for us as well. In each iteration, we know a good edge exists as well, because if you look at a subset of the edges, the average on that subset is good. Even though we don't know that subset, but we know a good edge still exists. So you can basically just apply BSS directly on our problem and get away with it. If I promise you the initial, if I change this condition to identity, not approximately identity, then you can just apply BSS to our problem, and then you would solve this. Okay, good. So the conceptual contribution of the preprocessing part of our paper is basically BSS is actually more powerful than just applying it to graph sparsification. It's actually can be applied, we believe it can be applied very broadly to a lot of semi-random settings. And the technical contribution is basically two things. One is that, like I said, the total sum of your vectors is no longer identity. So, for example, that prevents you from using some of the sparsification techniques. And the other is we need to go in and basically adapt the analysis so that it works for this approximately identity case. So one thing that we need to do, for example, is in BSS, you can control the upper and lower barrier to move at roughly the same rate. But now you need to take into consideration like how close this is to identity, right? Basically, you cannot hope that these barriers would advance at the same rate because your underlying solution is not identity, right? So, but it's not very hard to take care of, and you can do that. And that concludes this part of the talk. And before I move to the next part, let me tell you the implication of this preprocessing algorithm to matrix completion. So basically, the entire argument of the paper goes roughly like this. So if P is greater than some value, say log n over n, then you know that there exists a set of good weights. Why? You can just put the weights 1 on the entries revealed by nature and put weight 0 on the entries that later added by the adversary. because a good set of weights exists by this problem that we just proposed, you can find a set of weights that's close to expander. And then, good. So the guarantee of everything I presented just now is you can find this another matrix W tilde such that it's close to the all ones matrix in spectral norm, and you can compute it in nearly linear time. Okay. And in the rest of the talk, I'm going to try to give you a sketch of why this condition is enough to prove that the weighted non-convex objective function has no bad local optima. Okay. Questions? Okay. All right, so now we're moving to the third part of the talk, which is to actually do matrix completion. Okay. Again, let's recall this weighted objective function. Let me rewrite it a little bit. So I'm going to rewrite it as the inner product of two matrices, which is just basically you look at them as if they're vectors, but they're weighted by W. Right? So these two are the same thing. M star is just ZZ transpose. So the previous non-convex matrix completion work already tells us it's actually sufficient that you just look at the first and second order condition for this local optima in the direction towards the optimum. Okay? Basically, you're just going to say, I'm at here and the optimum is there. I'm only going to examine everything that's happening on that direction, and that's fine. That's enough to introduce a contradiction that X is not a global optima. Okay? So this is just a calculation. You're just going to plug this in. Just plug in X plus delta here, and take all the first order term related to delta, you get this. If you take all the second term related to delta, you get this. Okay. And if you stare at these first and second order condition, okay, you know the first order condition is 0 because the derivative is 0. And you know the second condition, second order, the Hessian in this direction is at least 0. A lot of these terms are in common, so you can actually combine them and cancel them a little bit. Recall that delta is equal to x minus z. So let me use some shorthand. Basically, A is the first order approximation of xx minus zz. And B is the actual matrix, which has this annoying second order term. And the first order condition just says AB equal to 0 under W, weighted by W. And the second order condition, if you plug it in, it roughly says this. Okay. So this slide is my very poor attempt of trying to convey to you how non-convex matrix completion works. This is not the analysis in the very beginning, and it has adapted several versions. But now I'm happy to say that it can fit in 2 slides, but you might need to stare at it for some time to convince yourself this actually works like this. Okay. But so far, I haven't used anything fancy. I just said, look at the first and second order condition in the direction of towards the optimum, and cancel a bunch of terms. Okay. And this is all we need to move on. So B is just this thing, the xx minus m star thing we have. Okay. So this is the condition we have. Turns out from this, if W is the all ones matrix, which means the samples are uniform, this is sufficient to show that XX transpose equal to M star. That is, you recover M star exactly. Why is that? Because you can show that the Frobenius norm of delta delta square is at most twice that much of this. Okay, so I'm not going to show the proof of this lemma, but what happens is essentially you need to find the right Z to align to. So basically, given an x, you are going to rotate z a little bit to minimize this delta. And then you can try to patch a bunch of things into squares and throw them away, and whatever left is this term. Okay. If you combine these two conditions, let's say W is all ones matrix, it's the old proof, then that shows you M star equal to XX transpose, right? Because this first term is going to knock out 2 copies of this term here, and then you get minus M star minus XX transpose is greater than or equal to 0, so this thing in the middle must be 0. And that, I believe, actually shows you if you do uniform sampling, That's not true. I want to say that you don't need regularization, but you actually do if the P is not large enough. But so yeah, anyway. But in this work, all that we need to show is for specific low-rank matrices like delta and M star minus XX transpose, the weighted norm under W is similar to Frobenius norm. Okay. When you're taking samples uniformly at random, this just follows from matrix concentration inequality. But now we need to replace them with deterministic condition. That is, the spectral norm between W and J, or one's matrix, is small. Okay? And this is the lemma we use in the paper. Basically, like I said, it relates the norm of the norm of a low-rank matrix under weight W and the Frobenius norm to the spectral norm stated here, and some other term that's related to like the max row norm of X and Y. Okay. Yeah. This also justifies why you need to do regularization, because one of these terms come from the incoherence, and the other one is your matrix, and then you need to basically take good care of it, so make sure it doesn't blow up. But anyway, I'm not going to dive into the detail of this. But essentially, this is the most crucial thing that you need to change in the analysis. You need to replace the matrix concentration bounds with this spectral norm condition. Okay. Good. And finally, we get that after the preprocessing algorithm, any local optima of fx actually satisfy this condition. It can recover the. That doesn't make sense. It should be this. So, good. So my residual, the Frobenius norm squared of my residual is at most epsilon of the original thing. Good. Yeah, I proved this. But yeah. Okay. Good. Questions?
Just trying to pass the lemma. So why do we get again the W minus J is small?
Because nature revealed enough sample to you. If you only look at the sample from nature, it gives you an expander. And the preprocessing algorithm can recover expander from expander plus garbage. And that's why.
So for us, J is a risk. just trying to understand.
J is all one matrix.
Not a rescaled version of the other one?
No. W does your rescale for you. So W is any non-negative weights you can put on the samples, right?
So J is not P times the old one?
No, W is like 1 over P times.
Okay. That's why you put it on my English.
Yeah, but you're right. You need to put it somewhere, right? We put it in W.
Okay.
Yeah, I'm happy to tell you more offline about this. Good. Okay, now I'm just going to conclude. So basically, our main results are threefold. First is we pose and study non-convex matrix completion and basically question this commonly used assumption that Pij equal to P, and we'll say it's at least P, what happens. And we show counterexamples that the existing non-convex approach would not work. And then, in light of these negative results, we propose a preprocessing problem, and we show that you can solve this in nearly linear time and get some good spectral property from your weight matrix. And then using that property, you can show that the non-convex objective has no bad local optima. So you can just run gradient descent or alternating minimization on it, and you would be fine. Good. So the other main conceptual contribution of this work is basically we're trying to bridge together two relatively young fields. One is spectral graph theory that develops fast algorithms based on the connection between discrete and continuous optimization. And the other is theoretical analysis of non-convex algorithms. Basically, in this work, we showed that you can get an efficient algorithm by mostly using non-convex approach, but run a very lightweight convex optimization in the beginning. So you sort of like get the better out of both. Good. Okay. Open problems. So I have two of them. One is that actually this should be exact recovery. There is something that I'm sweeping under the rug here. Previous results were able to show that if P is large enough, you can actually exactly recover M star. But in our paper, we can show that. And I have a counterexample of that actually being false. So you cannot recover it exactly. You can only recover it up to some epsilon in Frobenius norm. And behind that is really this question, is how much samples do the adversary needs to reveal to you so that you can actually get stuck in a local minima that's close to the global optima? Okay, and we don't know the answer to this question. What we're really hoping to say is that the adversary must reveal, what I really want to say is 50% of the samples needs to come from the adversary for the adversary to mess you up. Okay, if only 1% is coming from the adversary, then you are still fine. I really want to prove that statement, but I couldn't, so it's an open problem. And then I think that the more important one is the conceptual one. That is, can you apply the Batson-Spillman-Srivastava framework or packing SDP solvers in general to more semi-random problems? Okay. And I know the question is yes, so I know one other problem that you can apply this to. And I'm pretty sure there are plenty more. I mean, it's just packing SDP solvers, right? So now you can solve them fast enough. You can do magic with them in practice. And that's it. Good.
Can you do anything if you just get a p fraction of your matrix, but it's not random entries? Like a dependence p fraction?
Well, for example, if I never observe entries from one row or column, then there's no hope I can recover. Right, even if it's rank 1. So
maybe a p fraction from each row and column or something.
That's also, yeah, you need to be right. So good. No, because for example, you could have, if you only observe entries from the diagonal blocks, then you can't do it, right? Like, the way I think about it is like, think of the rank 1 case. What you can really do is if you observe these 3 entries, and it's like this triangle thing. If you have 2 edges, then you can recover the 3rd edge. So what you're really saying is your graph needs to be connected in some sense. But every node has degree at least Pn doesn't guarantee the graph to be connected, right? So you need to be careful about what conditions you put on this. Yeah.
Okay.
All right, thanks very much.